Hey, what's up everybody? In this video, I want to spend some time discussing electrophilic aromatic substitutions. Specifically, I want to talk about nitration reactions, right? So, what is a nitration reaction? What does it mean when you say something's been nitrated? In order to probe all of these questions, the first thing I'd like to consider is benzene. So, here's benzene. And as usual for my electrophilic aromatic substitution series, I've drawn in a hydrogen on this benzene. Now, let's say you took this benzene and you've reacted it with two acids, specifically with nitric acid and with sulfuric acid. All right, now if you do this reaction under the right conditions, under the right circumstances, what you should end up getting is nitrobenzene. So notice all you did was you exchanged a hydrogen for an NO2 group, for a nitro group. All right, so this process outlined here is essentially the nitration reaction. All right, so that's the reaction. Why don't we spend some time talking about the mechanism? Now, before EAS can actually occur, we actually need to generate a good electrophile that's suitable for EAS. And to explain how we can generate a good electrophile, I want to begin this discussion by talking a little bit about nitric acid. All right, so here we have the structure of nitric acid. Notice that we have a central nitrogen atom with a positive charge associated with it. And then we have that nitrogen double bonded to an oxygen. And that nitrogen is also connected to another oxygen that has a negative charge associated with it. And then this nitrogen is also connected to an OH. So the first step in this reaction actually has to do with this oxygen right here, the oxygen that's already connected to a hydrogen. You see, on this oxygen, there's actually two lone pairs. Now, one of these lone pairs is actually going to reach over to the sulfuric acid, right? This is sulfuric acid, and it's going to deprotonate that sulfuric acid, all right? So nitric acid is going to deprotonate sulfuric acid, and so then over here, notice now we have the protonated nitric acid, right? Over here, we had an oxygen with one hydrogen on it. Now we have that same oxygen with two hydrogens on it. All right, so notice now this oxygen also has a positive charge associated with it. And since sulfuric acid became deprotonated, now we have hydrogen sulfate, sometimes called bisulfate. All right, so again, in this first step, we're really trying to generate a good electrophile that is suitable for electrophilic aromatic substitution. Now, I want to just bring your attention to the protonated nitric acid really quick. There's a couple of things that are going on here. First off, remember that oxygen with the negative charge on it? Yeah, so if we look at that oxygen again, there's a lone pair on this oxygen. There's actually three lone pairs, I suppose, but we really only need to consider one of these lone pairs. Now, one of these lone pairs, they're actually going to fold in, so we get another bond here between the oxygen and the nitrogen. Now, when this lone pair folds in, this HOH group gets kicked out, right? So here we have the bond between this nitrogen and this oxygen. The electrons in this bond are actually going to fold back onto this oxygen here. So this whole HOH is going to get kicked out as a leaving group. Now think about it for a second. HOH, what is that? HOH, oftentimes called H2O or water. So we're actually kicking out water here as a leaving group. Now, when you're considering leaving groups, one of the things that a lot of organic instructors will tell you is that a good leaving group is the conjugate base of a strong acid. So the question is water, right, is HOH, is water the conjugate base of a strong acid? And the answer is yes. That strong acid would be hydronium, H3O+. So H3O+ is a strong acid. Its conjugate base is water, right? It's H2O. So this is actually a pretty good leaving group. Something else that makes this a particularly good leaving group in this case actually has to do with charge. So notice again, our central nitrogen atom has a positive charge associated with it. Also, this oxygen over here has a positive charge associated with it. Now, in chemistry, physics, science in general, opposite charges attract, but like charges repel one another, right? So because we have a positive charge adjacent to another positive charge, that also sort of makes this leaving group here an even better leaving group, right? Because this positive charge is going to sort of push on this positive charge, all right? So once this lone pair folds in, we're going to get a double bond between this oxygen and this nitrogen, which is shown here. And when this happens, we're going to kick out water as a leaving group. All right. So once we form this double bond here between this oxygen and this nitrogen, we get something that looks like this. An oxygen double bonded to a nitrogen, double bonded to another oxygen. And I don't know if you can see this very well or not. Let me fix my lighting here a little bit. There is actually a positive charge associated with this nitrogen here, right? So this structure I have here, this oxygen double bonded nitrogen, double bonded oxygen, with a positive charge on this nitrogen, this species here is referred to as the nitronium ion, all right? The nitronium ion is characteristic of the nitration reaction with regards to electrophilic aromatic substitution. That's to say that anytime you're doing a nitration reaction, specifically an EAS nitration reaction, you're probably going to form this nitronium ion, because this nitronium ion is actually going to serve as our electrophile. All right, so we've generated a decent electrophile here. Now benzene can come by, and it's going to use 2 pi electrons. And those pi electrons are going to reach out and grab that nitrogen. And when that happens, let's take a look at this double bond here. So we have a sigma bond. One of these is a sigma bond. The other one's a pi bond. Those pi electrons here are going to fold back onto this oxygen here. All right? So we're going to have something that's aromatic react with an electrophile, and that's going to yield something that is no longer aromatic, right? So this is essentially our rhenium ion here. All right, so we have something that's no longer aromatic, but we're going to restore aromaticity through a deprotonation step. So remember earlier when we generated this species here, this hydrogen sulfate or this bisulfate? So it's going to come by, and a lone pair on this oxygen, remember this oxygen was deprotonated earlier, a lone pair on this oxygen is actually going to deprotonate the hydrogen that we drew in earlier. So this is the hydrogen connected to the carbon that's connected to our electrophile. All right, so this chemical species here, this hydrogen sulfate, it's going to deprotonate that hydrogen. And then these electrons here in this hydrogen-carbon bond, they're going to fold back into the ring, and that's going to restore aromaticity, right? So we've generated nitrobenzene, and we've also regenerated sulfuric acid. So because sulfuric acid was not consumed in the overall process of this reaction, sulfuric acid actually serves as a catalyst. It's a catalytic acid in this nitration reaction. All right, so that's electrophilic aromatic substitutions. Specifically, we're talking about nitration in this case. The first thing we did is we had to generate a good electrophile. All right, so we did that by reacting our nitric acid with our sulfuric acid. Then we got a protonated form of this nitric acid, right? And so this lone pair on this oxygen is going to fold in, kick out water as a leaving group, and that's going to generate our nitronium ion. Again, it's the nitronium ion that's characteristic of nitration reactions, and it's the nitronium ion that's going to serve as our electrophile. Once we've generated this electrophile, we are now ready to begin electrophilic aromatic substitution. Benzene will come by. Benzene again is aromatic. It's going to reach out, grab this nitronium ion, and so we're going to go from something that's aromatic to something that's no longer aromatic, but then we're going to restore aromaticity through a deprotonation step, and that's going to give us nitrobenzene. All right, so that's really quick and dirty nitration. Stay tuned because I think in the next video I'm going to discuss sulfonation. So if you have any questions or comments about any of this, let me know in the comments section below, and thanks for watching.